Welcome, Mathophiles. On this part of Adventures in Modern Algebra, we are going to review Congruence Modulo N. So this is an example of an equivalence relation we often cover in the proofwriting course, but we'll review it again in case you haven't seen it or have forgotten about it. Of course, we have to give the definition first. N is a natural number, which means that it is an integer that is positive. We're going to add the extra restriction that is greater than 1. Then the definition is that for any two integers, say little a and little b, we say that a is congruent to b modulo n. That's how we say it, and we write this symbol. If and only if a minus b is divisible by n. So in case you don't remember what this division symbol means, it means that a minus b can be written as a multiple of n. So n times q for some integer q. That's what that means. So this is how we write the equivalence relation. Notice this little n is always going to be a fixed number, and it's little a and little b that vary. And so the first fact we have to point out is that this relation, congruence, is an equivalence relation. And in case you don't remember what that means it must be reflexive, symmetric, and transitive. And what does it mean for reflexivity to hold? Well, it means that everything is related to itself. So A is congruent to A modulo n. But what does that mean? Well, by this definition, that means n has to divide a minus a. Oh, but a minus a is equal to 0. Which means that n has to divide 0. And if you check the definition we had earlier, well, it's easy to write 0 as a multiple of n. You just write 0 equals 0 times n, and you're done. So n divides 0, which means n divides a minus a, which means, yes, a is congruent to a modulo n. So this equivalence relation is, in fact, reflexive. So we've got one of the three properties we need. Oh, wait, but there's more. We have to check that it's symmetric, which means that if a is related to b, then b is related to a. In the context of this equivalence relation, or this supposed equivalence relation, that means that if a is congruent to b modulo n, then b is congruent to a modulo n. Well, what does it mean for a to be congruent to b modulo n? It means that n must divide a minus b. And what does it mean for b to be congruent to a modulo n? Well, we need to show that n divides. So we have n divides a minus b, and we need to show that n divides b minus a. That's the step we need to show. If we can show that, then we've shown that this symmetry property holds. So suppose that you have two integers a and b, such that a is congruent to b modulo n. Well, then n divides a minus b. Well, if n divides a minus b, then a minus b is q times n for some integer q. That's just the definition of divisibility, and this is just the definition of congruence. Well, how are a minus b and b minus a related to each other? Well, b minus a is the negation of a minus b. And so b minus a is just negative q times n. Oh, look, negative q is an integer. Oh, so b minus a is an integer times n, which means n divides b minus a. And so b is congruent to a modulo n, which means that congruence modulo n is in fact a symmetric relation. So we have two of the three properties to be an equivalence relation. What is the third property? That's right, we still have to show that it's transitive, so we have to show transitivity holds, which is that if a is related to b and b is related to c, then a is related to c. In other words, if we have three integers a, b, and c, such that a is congruent to b modulo n, and b is congruent to c modulo n, then a is congruent to c modulo n. Note, of course, this means that we're assuming n divides b minus a, and n divides c minus b, and somehow we need to show that n divides c minus a. If we can do that, then we've managed to show that this relation is transitive. Well, what does it mean for n to divide b minus a? Well, it means that b minus a is equal to some integer times n. Let's call that integer q because we lack imagination. What does it mean for n to divide c minus b? Well, it means that c minus b is equal to r times n for some integer r. Why am I using r? Well, because we can't use q because we're already using q. And if I were to use q here, I would be adding the additional assumption that c minus b is equal to b minus a. And we don't want to make that assumption because these are supposed to be three arbitrary numbers with the only thing we know about them is that they satisfy these two properties. And so if this were a q, we would actually be assuming that c is related to b in the same way that b is related to a. So let's not do that. All right, so these are our two assumptions. Somehow we need to get c minus a to be a multiple of n. Now this proof is kind of a magic trick. Once you've seen it, you know the trick, but the first time you see it is kind of funny. So what do? Well, we cleverly rewrite this as a sum of these two numbers. Namely, you see that minus b plus b is 0. So you just add these two numbers together. Quite literally, if you add these two numbers together, you get c minus a. On the other hand, since b minus a is equal to q times n, and c minus b is equal to r times n, this calculation is equal to rn plus qn, while at the same time equal to c minus a. So you now see that c minus a is a sum of two multiples of n. However, since both these terms have a factor of n, you can factor it out. And once you factor out that factor of n, look, I have r plus q. R was an integer, q is an integer. R plus q together is also an integer. So c minus a is an integer multiple of n, which means that n divides c minus a, as we wanted to show, which means that a is congruent to c mod n. So we got the divisibility property we want, and hence we got the conclusion we want. So every element is congruent to itself. If a is congruent to b, then b is congruent to a. And if a is congruent to b and b is congruent to c, then a is congruent to c. Notice in all these examples, n is a fixed positive integer. We're only working with one equivalence relation. And so this forms a good example of an equivalence relation and a proof of how to show something is an equivalence relation. Of course, it is worth checking the book because this is slightly less detailed than how I would normally expect you to write a proof. As you'll see, what am I lacking? Well, I'm lacking sentences and paragraph structure. I really ought to have paragraphs saying, first we show that the relation is reflexive, let a be an integer, and then you do the proof that a is congruent to a mod n. Then you'd have a second paragraph that says, now we show that the relation is symmetric. Let a and b be integers. Suppose that a is congruent to b mod n. And then do the calculations. And so on and so forth. And then you'd have a concluding sentence that says, therefore the relation is an equivalence relation. But since it's a review, I didn't want to go through the full detailed proofs. We will see plenty of full detailed proofs as the course goes on. Now here we get into some material that's considered somewhat review, but you might not have seen it in a previous course, so it's worth going over it. It's actually very important for this course. It's the following two properties of addition and multiplication with respect to this equivalence relation. namely that for any two integers, a plus b is congruent to b plus a, and a times b is congruent to b times a. Of course, it's always worth unpacking what a statement means. What does it mean for a plus b to be congruent to b plus a modulo n? Well, that means n divides the difference of the left-hand side minus the right-hand side, which means n divides a plus b minus b plus a. But it's not too hard to see that this minus sign distributes, so you have minus b minus a here. And then you see that a minus a is 0 and b minus b is 0. And so this right-hand side is just 0. And we already showed that n divides 0 for any integer n. And so this first claim is trivially true. So here's an attempt at a formal proof. Since n divides 0, which is equal to this summation, or this difference of sums, we have a plus b is congruent to b plus a modulo n. It's not technically a formal proof because one ought to have started with let a and b be integers, right? The more important proof is the second claim. So a times b is equal to b times a. Well, what does that mean? Again, n divides the difference of the left-hand side minus the right-hand side. So a times b minus b times a. So you just took the musical group ABBA and you added a minus sign in the middle. Oh, but of course, silly us, multiplication's commutative. A times b is equal to b times a. The same thing happens again. So we see that addition and multiplication are both commutative with respect to this congruence relation. Other facts that are true is that for any three integers, if you compute a plus b plus c, then a plus b plus c, you get the same thing when you look at the congruence classes. These two calculations are both congruent modulo n. And the same thing is true if I replace plus with multiplication. The proofs are similar to what I just did, so it's not exactly enlightening. The reason why we state these facts is because we use them later. The other silly fact that seems trivially true is that 0 plus a is congruent to a modulo n, and 1 times a is congruent to a modulo n. So none of these seem that surprising, and none of them are that hard to prove. Continuing the list of properties that would surprise nobody, if you have three integers, a times b plus c is congruent to ab times plus ac modulo n. And if you add a number to its negative, you get 0 modulo n. But now we get to something new. For every integer a, if the greatest common divisor of a and n is 1, then there exists another integer b such that a times b is congruent to 1 modulo n. As an example, take n equals 10 and say a equals 7. The greatest common divisor of 7 and 10 is 1. This is saying that there exists an integer b such that 7b is congruent to 1 modulo 10. Notice that, in some sense, this is saying that 1/7 exists modulo 10 as an integer, which is kind of weird. Of course, this is actually bad math to state it that way, and I won't state it that way throughout the rest of the course. But the idea is that somehow you do have multiplicative inverses sometimes with modular arithmetic, even though classically, for integers, if I solve the equation 7b equals 1, b has to be 1/7. I can't solve it over the integers, I need the rational numbers. But this statement says that occasionally you can solve an equation like this in modular arithmetic. In this case, you can check that b is 3, because 7 times 3 is 21. which is congruent to 1 mod 10, because when you divide by 10, you get a remainder of 1. So now, of course, we check, how do you prove such a result? Well, what do you need? You need n to divide 1 minus a times b. Note right now, we don't know what b is yet. We want to find b. But suppose we had it. We know we would need this property. The other thing we know is that since the GCD of a and n is 1, 1 is a linear combination of a and n. This is the Bazoo property. So let's call the coefficient of a b and the coefficient of n c. Of course, this kind of cheatingly gives the game away by doing it this way, but you see what happens. If I move ab over to the other side as 1 minus ab, I get 1 minus ab equals a multiple of n. So 1 minus ab is n times an integer. So we found the right value of b that would work, namely any Bazoo coefficient when we write 1 as a linear combination of a and n, where these coefficients are also integers, and we know by the Bazoo property that this has to happen. So there's our proof. Since the greatest common divisor of a and n is 1, 1 is equal to ab plus nc for some integers b and c. This is the Bazoo property. And note, by using the extended Euclidean algorithm, you can actually find this b. Well, then n times c is equal to 1 minus ab. So n divides 1 minus ab. Therefore, 1 is congruent to ab mod n. Why? Because that's the definition of congruence. And what was our goal? Our goal was to find an integer b such that ab is congruent to 1 mod n, and we found it. Therefore, we proved the result. There existed a b with this property. And here is a bonus result that's not in the book, but I thought it would be worth pointing out because it's proven in a similar manner. If the GCD of a and n is some integer d that's not equal to 1, then you can find an integer b such that b is not congruent to 0 mod n, but a times b is congruent to 0 mod n. This is a fact that's sometimes used in other parts of the course, but it's kind of interesting to note. So you see this dichotomy that's kind of weird. If a is coprime to n, which means that the greatest common divisor is 1, then you've got these multiplicative inverses, and if it's not, then you've got these things that when you multiply by, you get 0, but neither factor, a or b, is congruent to 0, which is just kind of weird. That doesn't happen with integers. The proof is very similar. Basically, by the Bazoo property, you write d as a linear combination of a and n. And since d divides n, n can be written as q times d. Then you just take as and you multiply by q. Well, then you can rewrite as as qsa. You can bring this nt to the other side and replace sa with d minus nt. Distribute the q to get qd minus nqt. Remember, qd is equal to n. And now look, everything's a multiple of n, so you can factor it out. Oh, but n is our modulus, so this is actually just 0. So we get qsa is congruent to 0 mod n. So if you let b equal to q times s, then you just found a number with this property, which is kind of neat. And so this is an example of a constructive proof because you find s using the extended Euclidean algorithm, and q is just n divided by d. Now, of course, there's still some argument here where you have to prove that q times s is not congruent to 0 mod n, but that's not that hard to prove.